In this part 2 of 3, we will hack the Servant RTL to add more GPIO pins.
All right, this video is going to pretty much be a stream of consciousness. Hopefully, we succeed at adding more bits, GPIO bits, to the SERV processor. And here we go. So currently where we're at is that we have one Q output of the Servant wrapper around SERV. And that's the default case. And just show that we can still simulate that. We've got a nice simulation running. All right, so that's a good starting point. So we'll have that starting point there. We'll run the sims, and over here we're gonna edit a test bench, and we're gonna edit some or all the files in Servant. Let's see what we need to touch. All right, so let's start with the test bench, which is right there. And so what we want to do is we want to change Q from being a single bit. We want to change it to being a bus. Actually, I don't want to do that. I want to leave Q there because Servant is used by thousands, millions of people. And so let's just add a Q bus signal here. And a Q bus here. That leaves the Q unchanged. So people who are using it will continue to be able to use the single bit Q. And we'll do a wire. So we want to call it 0 Q bus. There we go. All right. Yeah. Why not? That looks fine. All right. So now let's drop down into APB Savant. So let's open APB Savant. And here we are. Here's our APB bus. And here. All right. So we've just added it as an output port. Let's see. Let's find out where Q is being used. And right here, it's coming out of this GPIO block. So that's where we're going to have to hack away. Dot, let's follow their convention coming out of that block. GPIO plus, why not? Underscore. Plus. Now let's get rid of that. No underscore. Comma. I think that looks good. Now let's drop down into Savant GPIO. We gotta come up with a GPIO bus. All right, so let's drop down into Savant GPIO. Is that all there is? That's all there is. All right, we pasted it in from above, so we should get the spelling right. All right. So let's put a begin and an end around this because we'll have two lines here. And we'll say GPIO bus is equal to dat. So it looks like this data bus, though, we've already done some trimming to reduce this down to a single bit. So let's increase that to, 32 bits. So now this data bus that's coming from the SERV processor is going to be 32 bits instead of just the 1 bit. Okay. So now let's go back up to Savant and find that signal here. So that was the signal there internally. So externally, it's this guy here. So let's find him. Let's change him to 31:0. Let's find out where else it's used. And so it's coming out of this Servant mux. All right, so I think we want to go in and we want to find that signal inside of Servant mux. So let's go to Servant mux, which is here. And when we find it, it's here. So we want to make this guy, we want to call it 0. All right, let's see. And so here we've got this assignment statement where it's just taking the first bit of this data bus. Let's take the full, all of that data bus. Let's take a look at it too. So it's 31 bits coming in, and previously they were just taking the bit 0, and now we're taking 31 down to 0. So that should, I think, do what we need. Um, yeah. All right, so this is out. So let's go to T. Let's see. It looks like a few that I made some changes to, but I did not save. Let's save that. Save that. Okay, it looks like everything is saved. So let's go to the sim area. Let's see if it compiles, and it'll probably yell about something. Warning, port 6. Something's going on in 135 APP Servant. So let's get back to here. Let's add some line numbers. Let's go down to 135. Let's see, let's follow this signal. These are 31 bits. All right, so I think this guy here. Um, let's go into Servant GPIO. And well, isn't this interesting? Oh, no, I did. I think this is probably the problem right here. Now we want this guy to be this. Right? 31 to 31. That's a silly mistake. Okay. Output is 32 bits as well. Okay, let's give it a shot again and see if that does any better. Let's go back to this tab with our compiler on it. Hey, look at that. Now let's go and change the test bench a little bit. All right, so this is the test bench right here. Select it, paste it. Let's see. There we go. Let's not test the queue anymore. Let's go after the queue bus. So whenever there's a change on the queue bus, so let's OX just to show that's a hex number. 08X. That's 32 bits of hex digits for queue bus. Now good. Let's compile again. And let's there on the sim. Okay, so now we're getting the 8 bits out. Currently, only the LSB is changing. We'll have to change that with a change to the software, which will be in the next part of this 3-part series. So I think I've got the code working kind of nicely. So what we want to do now is we want to edit the cape. Um, HDL, cape, HDL cape. That's what we're going to edit. And now we're at HDL cape. Let's get rid of that because we do not need the timescale. I recommend you only put that in your top level test bench. Scroll down, scroll down. What am I looking for? Forget it. Let's look for APB civil. Here we go. And we've got now Blink and XPV. Call it a Blink bus. Like that. Sure, why not? Okay, let's find wherever Blink is being used here. Blink. Right. We're gonna call this guy 31:0. So let's change the size. All right, so now we got Blink. Whoa, whoa, whoa. Forgot that comma. Okay. So Blink underscore bus. Okay, so now let's search for Blink again. Find out where it's used. Right here. So this statement here is the one that the selects between the processor driving the GPIOs and our logic. And so this is where we'll be hacking. So let's comment out those 2 lines so we can get back to it if we need to. Let's see if we want to bus. Okay. So I'll let the processor. These 28 bits. Okay. So that equals 16 plus 28 equals 38, 44. Okay. So here we're getting actually a bit 15. So I think subtract off 3 more of that because this. So this mental gymnastics is getting to me. There we go. I think we're good. Okay. So I think we've done all we can do here. Let's go to get status. So we change the cape. We change this APB server, we changed the GPIO, we changed the mux, we changed the test bench. Earlier I changed this guy here. So let me, by mistake here. So let me fix this. Copy that. And what I had done was I made an HDL. So let's move. And then git move. And git status. Okay. And let's see. Oh, we have to sign in. And let's drop down into the repo. And in the repo, let's drop down to pipelines. And it's running. Okay, this build passed. So let's connect up the Beagle Fire to the device manager. See what COM port it comes up on. Get buddy ready. On port 19, it's typical for my system. Increase the baud rate to 115, 200. Say open. Um, and all I'm really interested in is this IP address. Okay, 172.16.07. Now we go back over to here. New tab. SSH. Let's see if it works. Paste. Excellent. In front of that, let's put in the Beagle that. And return. Enter the password, which is right there on the screen. Type in wget. Let's go back over here. Click on this, right click on archive, left click on copy link address, right click, paste, and let's see, minus capital O archive.zip, and return. And, clean up. The zip archive. Synthesis logs. This is the file we want to use. Let's see, I've got in my history command. I think change again. Grab change. All right. And let's see if we can do this. All right. It's this one here. So 515. So exclamation mark and 515. And so this will conclude this video as we burn the image of the new gateway to the BeagleV Fire. And so in the next video, we'll write some software that we'll be able to load onto the servant of the APB bus, and that ought to be able to make the LEDs do different things. I think that's it.